Good morning, sir. My name is Yal Monica. I am from second year ECA section. Today, I would like to explain about ring counter design, operation, and its applications. The outline of this topic is introduction to sequential circuits, definition of ring counter, working of ring counter, table of ring counter, types of ring counters, applications of ring counters, advantages of ring counters, limitations of ring counters, designing a ring counter, troubleshooting tips, real world examples, and conclusion. Introduction to sequential circuits. A sequential circuit is a type of digital circuit whose output depends not only on the current inputs but also on the history of past inputs. This means that sequential circuits have memory elements that store past states, enabling them to remember previous inputs and respond accordingly. This contrasts with combinational circuits where the output is solely determined by the current input. The block diagram of the sequential circuit consisting of combinational circuit and memory element. Memory element is a flip-flop or shift register. Flip-flop is a 1-bit storage device. The main difference between combinational circuits and sequential circuits is the combinational circuits, the output only present on the current inputs, whereas in sequential circuits, the output present not only on the current input but also on the past history of outputs and the clock signal. Sequential circuits requires a clock pulse, whereas combinational circuits doesn't require any clock pulse and it requires enabling input. What is a ring counter? Ring counter is a type of sequential logic circuit that consisting of flip-flops connected in a cascading manner. It cycles through a predefined sequence of states, making it useful for counting and sequencing tasks. Understanding its structure is a key mastering to its use. Ring counter is used to count the numbers. If it is a 4-bit ring counter, it counts 2 power 4 bits, that is 16 numbers it will count. Uh, if a 4-bit ring counter, it requires a 4 flip-flops and 4 clock pulses. For each clock pulse, it one is shift from one flip-flop to next flip-flop. How does it work? The operation of a ring counter is straightforward. It shifts a single 1 or 0 around the ring of flip-flops. Each clock pulses moves the 1 to the next flip-flop. This creates a repeating sequence which is perfect for various applications in electronics. It consisting of clear input and clock pulse. Initially, the all flip-flops are cleared by the cleared input. For the first clock pulse, the one shift from Q1 to Q2. For the next flip-flop, the one shift from Q2 to Q3, and the output of last flip-flop is connected to the input of first flip-flop. This will repeat the system for the number of bits. To understand the operation of ring counter, let us assume we have 4-bit ring counter and it consisting of 4 flip-flops and it is labeled as Q0, Q1, Q2 and Q3. For initial clock pulse, Q0 will set to 1, all are zeros. For the second clock pulse, Q1 will be 1 and remaining all are zeros. For the third clock pulse, the one shift from Q1 to Q2 and all are zeros and it repeats for 4 clock pulses. For the fourth clock pulse, the one shift from Q3 to Q1. The system will bring back to the initial state and it repeats for 4 clock pulses in a cyclic manner. There are mainly two types of ring counters, the simple ring counter and the Johnson counter. The simple version has one in the ring, while the Johnson counter has a more complex feedback mechanism, allowing it to count in a different manner. Both have unique applications. Applications of ring counter. Ring counter are used in various applications, including digital clocks, sequence generators, and LED casers. They are ideal for tasks that require a specific sequence of operation, making them versatile in both consumer electronics and industrial electronics. Advantages of ring counter. Some advantages of ring counter includes this simplicity, ease of design and easy of design and low power consumption. They are also reliable for counting purpose and can be implemented easily in various digital circuits, making them a favorite among engineering. Despite their benefits, ring counter have limitations. Uh, They can only count up the number of flip-flops used, and the sequence can be predictable. It's essential to consider these factors when deciding if a ring counter fits your project needs. Designing a ring counter. When designing a ring counter, start with determining the number of states needed, then choose the appropriate flip-flops and configure them in a ring. Be mindful of the clock timings and reset conditions to ensure smooth operation throughout the cycle. Let us assume we have to design a 4-bit ring counter. Then we require 4 flip-flops. To design a ring counter, we can design a ring counter either by using D flip-flops or JK flip-flops, and we require 4 clock pulses. In designing a ring counter, the number of bits is equals to the number of clock pulses required. The 4 flip-flops are connected in cascading manner. The output of the last flip-flop is connected to the input of the first flip-flop, because the system will be feedback to the initial state, and it consisting of clock pulse for each flip-flops, and it consisting of clear for each flip-flop. Troubleshooting steps. If your ring counter is not working as expected, check for common issues like clock signal problems, flip-flop malfunctions, or incorrect connections. Simple debugging can often resolve these issues, allowing your circuit to function correctly. Real world examples. Ring counters are found in everyday technology, from traffic light controllers to game show buzzers. Their ability to manage sequence makes them invaluable in systems where timing and orders are crucial. Let's celebrate their impact on your daily lives. Conclusion. In conclusion, ring counters are a fundamental component in digital electronics. Their simplicity, efficiency, and versatile make them ideal for various applications. We hope you now have a better understanding of how they work and where to use them. Thanking you for joining us. Thank you.